All right. Before we get to our equations, I wanted to try and give you a visual for why we might care about this. So right here, you can see there's a piston being supported by the gas that's trapped in this metal cylinder here, and there's some under there. So this is all a closed system. So we have a piston, and we can change the amount of force we apply to that. And then here I have some water, which is quite warm. It's near boiling. There's a little bit of steam there. And we can see that if I change the temperature of the gas, I'm going to try to carefully do this so I'm touching the hot water, but not the metal. We notice the piston can do work on this chunk of metal. And in short, that's really what we care about in this problem. But in order to, in this class, we're going to try and understand engines, pistons and engines, and you got to start somewhere. So if we really want to understand why this piston goes up and down, we need to have a model that's somewhat accurate that describes how temperature changes affect the volume of gas. So let's get to the board and just do this. All right. So forget this section for a second. Let's focus over here. Focus over here for right now. Literally focus, computer. All right, there we go. So we've got Avogadro's number. So that's 6.022 times 10 to the 23rd. Sometimes you'll see this written with units, 1 over mole. Now, I want you to think about the term mole like the term dozen. So if I say I have 1 dozen eggs, I have 12 eggs. If I have 1 mole of eggs, that's 6.022 times 10 to the 23rd eggs. So mole is not really a unit, but yet it's, so it is and it isn't in that sense. But yes, it's basically a descriptive term for the number of particles you have. So you'll see it written here. I wrote out the whole word moles, whereas when you're doing calculations, you'll just use MOL. So you don't have to, you save a little time. You do this thousands of times, you're going to save a significant number of time. So we had a piston with some air molecules in it. The total number of molecules we're going to call capital N. The number of moles we're going to call little n. And so this helps you describe the number of moles. And this just ends up being a lot more manageable to work with than stuff that's times 10 to the 23rd. So that's why we do this. So 1 mole, right, would be 6.022 times 10 to the 23rd molecules. If you had 3 times 10 to the 23rd molecules, you'd have approximately a half mole. Molar mass. Now, if you've ever seen all the numbers on a periodic table, there's usually some carbon 12 or some 12.011 or something like that. Those numbers represent what is called molar mass, the mass of 1 mole of carbon, etc. And so the numbers from the periodic table, and we'll do examples with this later, will give you the grams per mole. And in a physics class, usually I'll just tell you the molar mass if that's going to show up in a problem, or I'll give you a mini periodic table or something like that. So don't freak out, you don't have to memorize the periodic table for test day. Let's say you have a massive sample, like say you had 126 grams of copper. All right, so that would be the mass. You could look up the molar mass of copper, and isn't that something like 63.5 or something like that? I don't remember. But so you could figure out the number of moles by looking up this number on the periodic table, then getting from the problem statement how much mass you have, and you could learn this, or you could know the number of moles and figure out how much mass you need. Now, the ideal gas law is given by these equations. Well, let's come back to the equations in a second. Let's focus on the assumptions. For the ideal gas law to be valid, we want to have a huge number of molecules. I'm going to remember to turn off this boiling water. Sorry, it's distracting me. Well, that's usually true. This is usually considered a big number to me. All right, so molecules move in random directions and random speeds. Okay, fine. The air molecules are moving all over the place in every which way at all kinds of different speeds. Molecules spend most of the time far apart. This is usually true. More on that in a minute. Collisions are elastic. We're assuming that when molecules collide, they conserve energy. We assume that intermolecular forces are completely negligible except when they're colliding. Obviously, as two molecules are getting close to each other, you might expect that, oh, the intermolecular forces might change things a little bit, but we're going to assume that's negligible. And molecules use up a negligible volume. So the actual molecules themselves have some volume, but we're assuming that's negligible compared to the volume of the container. Now, for reference, 1 mole of gas at STP, standard temperature and pressure, is what, 22.4 liters or something? So when you're thinking about this scenario, we had a small, let me just grab it. Oh man, partial vacuum. Okay. We have this little can here, right? You could imagine this is a small fraction of a liter, but it's probably more than 1/10 of a liter. It's probably, somewhere around 100 milliliters to 200 milliliters. So, right, we're expecting about well, you could figure out the number of moles in here, but it's probably maybe 0.1 or something like that, or sorry, I don't, let me, why did I say this? 1 mole is approximately 22.4 liters. So if we had about 0.1 liters, you could figure that out. It's about 1/20th of a mole. But so we do have a large number of molecules. So this checks out for our situation. The molecules, we're assuming that's true. They spend most of the time far apart. We're going to assume that's true for this situation. True, true. All right, and so this is probably true. Air molecules are pretty small. In certain cases, if you cram, if you're under a real high pressure situation with lots of gas in a small space, some of these things might not be valid. And if you're trying to understand that, maybe you could read about the van der Waals. We're not going to do that, but if you want to, it's on page 78. You can read about a more accurate model than the ideal gas law. Okay, so all that said, we're going to use one of these two equations most of the time. So in chemistry, you'll notice, so we say PV equals nRT, or you could say PV equals nKT. This one is number of moles, so let's maybe emphasize that. So the constant has units of moles in it, all right? This one is number of molecules. I think we called that blue N. So notice capitalization is going to matter a lot. Now, in chemistry, maybe you've seen, in chemistry, people use units of liters, ATMs, but we're not going to do that. Why? Well, let's think about it. We're talking about forces. Forces relate directly to joules. So if we want to relate, like we were talking about, a piston moving up and down with some force on it, force would relate to newtons. Newtons go straight to joules. So this is why we're going to try and focus on this one most of the time. So this is what I want you to think of as the ideal gas law. And then in a later chapter, this one comes in handy. So I'm just mentioning it. One handy conversion to know, so it turns out, oftentimes you'll hear about the liters of displacement in an engine. So if you like to think in liters, it turns out liters times kilopascals is 1 joule. And maybe I'll mention this, atmospheric pressure, we've kind of alluded to this a few times, I don't remember when, but notice standard atmospheric pressure is about 100 kilopascals. So a lot of problems that we do will probably be in units of 100 kilopascals or 200. So you could talk about it as 1 ATM, 2 ATM in your mind. All right, so that's, right, so 1 ATM, pressure has a lot of different units. But you could think of 1 ATM as being approximately 100 kilopascals. And then to get to joules, you could do this unit conversion. Obviously, you'd want to keep all the sig figs if you're trying to be accurate. I think that's enough on this. We probably better do an example problem in the next video.